Hello, this is just a quick video more than anything else, just to test my recording equipment after not using it for so long. So this is a very quick video about e to the x and showing how you can write it in two different ways. This is an extremely simple mathematical proof, but it is quite a useful trick to know anyway, so I'm going to get on with it. So, one way you can define e to the x is in this form. You can say that e to the x is such that any derivative, whether it's the first, second or the nth, any derivative of e to the x is also equal to e to the x. So if you differentiate e to the x, you get e to the x, and if you differentiate it again, obviously you still get e to the x. So I've written this in this form here, so no matter how much you differentiate it, you get the same thing. So that's one definition. Another way you can define e to the x is in terms of this infinite power series, so 1 plus x squared over 2 factorial, which x squared over 2 plus x squared over 3 factorial, x cubed over 6, up to x to the n over n factorial. And this is the way you can write it in terms of summation notation. So I'm going to try and show how that arises. So the first thing you would do is you'd assume that e to the x can be written as an infinite polynomial. That is to say that it can be written in terms of an x to the 0 term, which is just a constant, plus an x to the 1 term, plus an x to the 2 term with coefficients on the side like that. Now, this assumption, I'm hoping, if it's incorrect, will fall down and there'll be some sort of contradiction that arises. This might not necessarily be the case though, and I can't rigorously prove that e to the x can be written as infinite series, but what I'm going to do is show how the coefficients can be derived. So I'm going to show how you can get from this to this, and this is extremely easy to do based on this definition here. So what you do is, the first thing, we'll take this series and we apply the definition that I originally started off with. So I'm going to differentiate it, so just differentiating this series. So the constant term disappears, the x term on the a1x disappears as well, and we end up with a1. A2x squared becomes 2a2x, and I'm just differentiating using the basic power rule. And then obviously a(n)x to the n becomes na n(x to the n minus 1, so nothing difficult there. And then I can repeat this process and continually differentiate. So I'm taking the second derivative here, and then the nth derivative here. So all I've done is I've just brought it down. So this represents the constant term. This is what happens to the constant term. And you'll notice that you start off with a0 as the constant term, then a1, then a2, and then after m times you end up with am as the constant term. And in terms of the coefficient, this is actually m factorial, because the first time you just multiply by 1, the second time you multiply by 2, because which comes from the x squared term, and then you multiply by 3, which comes from the x cubed term being brought down, and so on. So you end up with 1 times 2 times 3 all the way up to m, so you end up with m factorial here. And you end up with some other terms as well for the non-constant terms. And I'm not going to worry too much about these, because they're not entirely relevant to the proof. Although this one is fairly noteworthy, that the x to the n term becomes x to the n minus m, because you've differentiated m times, and that you end up with n factorial over n minus m factorial. So this comes about because when you differentiate x to the n, you bring the n term down, then you bring the n minus 1 down, then you bring the n minus 2 down, and you do that m times. So you've got the n factorial, which is n times n minus 1 times n minus 2 all the way to 1, but then you want to get rid of the terms that you don't multiply by, which is the terms that are lower than m. So you take away this way, you have the n minus m factorial on the bottom to remove those lower terms. So this is just n times n minus 1 times n minus 2 all the way to n minus m. So that's what's going on here. And then any lower terms are removed. N minus m plus 1. That's what we're doing there, because you can see that this number is actually lower than the 2 here. Anyway, that's a little aside, but the point is we can use this constant term because it's easy to work with to derive the proof. So we can say that a0 equals a1 equals 2a2 equals and so on, m factorial a to the m. So why can we do this? Because, as I said before, e to the x is equal to the derivative of e to the x, which means that this series is equal to this series is equal to this series is equal to this series. And we can equate coefficients, so we can say that since each series has a singular constant term, then this term must be equal to this term, and must be equal to this term, must be equal to this term. So we can equate all the terms like this. and you notice that there's only one free variable here. So everything depends on a0 because a1 is equal to a0, and a0 depends on a2 as well because 2a2 is equal to a0, and so on. So everything depends on the variable a0. So we can take that into account, and we can rewrite the series e to the x in terms of this. So now we know what these coefficients are. We can go back to my original assumption, where I wrote it like this, and then fill in these terms in terms of a0. So we've got a0 here, and then a1 equals a0, so I'm going to put my a0 here. 2a2 equals a0, so a0 is equal, so a2 is equal to a half a0. That's where the half comes from. And so on and so on. So 1 over 3 factorial a0 for the 3 factorial a3 term here, and all the way to the 1 over n factorial for the nth term. I've got the nth term here, but it doesn't really matter. I'm just using a different subscript. So this is the nth term here. So you can see how this develops like that. But I've still got the a0 coefficients on here, and theoretically a0 could be any constant. But the way to sort this out is by taking a particular value of e to the x that we know, and the best one to take is obviously e to the 0, because we know that anything to the power 0 is 1. So if we take e to the 0, we get 1. So take this series and put x is equal to 0 in the whole thing. So e to the 0 is 1 on this side, and then on this side, all the x squared, x cubed, all the terms with x in it cancel. Well, not cancel, but they all disappear because anything multiplied by 0 is 0. So you just end up with a constant term here. So you end up with 1 equals a0, which is what I've got here. So we know that a0 is equal to 1. So then, taking that into account, since a0 is equal to 1, we can just substitute a0 for 1. So we've got 1 plus 1 times x, so x, plus half times x cubed, so half x cubed, and so on and so on. So we've written e to the x as an infinite series, this here. So the sum from n equals 0 to infinity of x to the power n over n factorial. Okay. Anyway, this has just been a very simple proof. I hope someone will find it useful. Thanks for listening. Right. What I've actually done is created a Taylor expansion around x equals 0 for e to the x. So my original assumption, I actually used Taylor's theorem, that e to the x could be written as an infinite polynomial. So if you want more information about these sorts of infinite series, look up Taylor polynomials.